To look at this law of conservation of angular momentum, we're going to imagine an ice skater spinning on ice. We're going to assume that the net torque is about 0 because essentially there's no friction between her skates and the ice. So over here on the left, we're calling this is her initial angular momentum. She has a rotational inertia of a certain value at this point in time because she has a certain mass distribution. Her arms are further away from her center of mass, and so that's affecting her moment of inertia. And she also has a certain angular velocity at that moment in time. At this later point in time, she's brought her arms in, and she has what we're calling L2, her angular momentum at this later point in time. Since the net torque is 0, we know that angular momentum is conserved. So her angular momentum on the left is equal to her angular momentum on the right. L1 is equal to L2. And so then that means that I1 omega 1, that product, is equal to I2 omega 2. And so let's talk about what happens as she's pulling her arms in. So like I was mentioning, remember that I is dependent on how far mass is from the axis of rotation. So if the mass is further away from the axis of rotation, we have a larger value of I. And in this case, since we're going, from the left-hand case to the right-hand case, she's pulling her arms in as she spins, which means that the rotational inertia decreases. So over here, I2 is a smaller value than I1. But we know from the conservation, the product of each side has to match. So that means that the angular velocity in case 2 has to increase for that product to match. And so she ends up spinning faster. So by changing that rotational inertia, it affected the angular velocity as well. Decreasing the rotational inertia increased the angular velocity. If she were to put her arms back out, then that would lead to a greater I and she would slow down again.